Now the floor goes to Bryan Ford. So Bryan, please.
Well, thank you so much. It's good, great to be here. Thank you for the invitation. Several of the talks, as I'm sure you've noticed this morning, today are on the topic of blockchain. This is, of course, the and that has been one of my main focuses recently. But just to and what I'm very excited about, and I'll tell you why I'm excited about it. But before I do that, I want to back up and just kind of introduce my what I do and my bigger picture goal. So I'm a security privacy person and decentralized system builder. So my main goal is to try to figure out how to first recognize that the information systems that we're building on today are mostly built around what I call weakest link security, meaning it usually requires an attacker to break only into only one system or one piece of software, or one weakest link failure to defeat the security of a whole system. And as our systems get bigger and more complex, they tend to get less secure, easier to break into, because they have more weak links that still require only one break to fall apart, right? And so this is very high level and abstract, but keeping it at that level, my goal for a long time, long before blockchain was a term, was to try to rethink systems, to figure out how to redesign systems from weakest link security to strongest link security, so that it would take an attacker would have to break several systems, several independent machines, or compromise several people or system administrators or whatever in order to break a system. And this is what I call the general distributed or decentralized trust model. Decentralized, focusing on not just geographically distributed, but distributing trust across multiple independent parties, right? And ultimately, my goal is to try to figure out how to scale systems, scale the security of systems along with their size. So clouds. Infrastructure, have developed really good ways to scale the throughput and capacity of systems to huge scales, but the security doesn't usually scale with it. The privacy doesn't usually scale with it. Like I said, it gets worse. How do we build systems whose security and privacy actually gets better with size rather than worse with size? That's my big goal, right? So just to briefly introduce my team, I've been at EPFL for about 3 years. This is my current team back at the DDIS, Decentralized Distributed Systems Laboratory at EPFL, who did all the work I'm claiming credit for here today. So that brings us to blockchain, right? So I mentioned I'm doing blockchain now. Why? Well, it's a huge hot topic, and it's certainly a bandwagon, likely a bubble that's going to maybe burst any day now. And there's, of course, a lot of noise around it. But at the same time, I think it has a lot of promise. So, of course, speaking of the bubble, I need to update this diagram, but the investment in blockchain technologies is exploding tremendously. It's really created a huge splash across many industries, and it's even kind of created a new form of investment based on tokenization or initial coin offerings. And I'm not going to talk much about this, but of course, at least this phase of decentralization really started with Bitcoin in around 2008, which was the first successful decentralized cryptocurrency. Right now, So from my perspective, Bitcoin, no piece of Bitcoin was new, but Bitcoin as a whole, the architecture was very new and interesting in the way it put together the different pieces. And it was, and also the impact of Bitcoin in the rest of the society and industry. To me, as a computer science, the most important thing that I think Bitcoin did was bring the idea of distributed and decentralized trust to the rest of the world. So it wasn't anymore just computer scientists that heard about some of these concepts. So I'll get back to that in a minute as well. But Bitcoin is not perfect either. And from my computer science perspective, I think Bitcoin is was very successful in some ways, but also extremely flawed, and a real interesting study in lots of wrong ways, or promising but extremely flawed ways to do things in terms of decentralizing trust, decentralizing collaboration, or as Peggia said, creating decentralized or distributed collective intelligence, enabling people to work together in a decentralized fashion. So I want to explore some of those issues in this talk. So I'm not going to give much of a tutorial on Bitcoin, just overview some of the very, very basics. And then I'll jump into what I think is, the challenges and what's new and interesting. So the basic idea of Bitcoin is, first of all, to create a digital currency out of information rather than physical goods. So with Bitcoin, there's no need for physical goods backing anything. Instead, it's based on ledgers, keeping track of who owns what in a completely logical information sense, just like banks have been doing for hundreds of years, including in Switzerland, especially where I live now. But the traditional way, ledger-based currencies would work is a bank enters some stuff on their balance sheet and promises to keep those entries secure and only update them according to the right rules. So Bitcoin and most any decentralized trust system wants to set the goal of saying, well, let's not have any single party maintain that ledger. Instead, let's distribute the ledger among a lot of parties, among individual participants. So in the case of Bitcoin, in principle, anybody can maintain a copy of the ledger, and everybody works together using a consensus algorithm to try to keep each other honest, basically. And so that's the basic idea, and I'm sure many of you have seen the diagrams of how the Bitcoin works, a blockchain works, and many similar blockchains. It's literally just a chain of blocks linked by cryptographic hashes that help ensure that if several parties agree on the latest block, then nobody can change anything farther back in history. And then each block contains a set of transactions, again linked together in a data structure we usually call a Merkle tree, and then that again contributes to its tamper resistance properties. Now again, these hash chains and blockchains like this and Merkle trees, these all existed long before Bitcoin, but Bitcoin, whoops. Wrong button. Bitcoin put them together in a very interesting new way. And as we've seen in the past few years, Bitcoin, as Bitcoin generalized beyond a cryptocurrency into a concept, a more general ledger concept that we realize, many people realize, could be used for a lot of different applications completely independently of cryptocurrencies. Things like managing ownership of names or digital works of art, or enforcing the terms of a contract digitally, what Ethereum does. Notarizing documents, managing, tracking the provenance of pieces or supplies or things like that. There's managing identity and allowing users to control what they disclose and what they don't disclose in identities, and managing data and how it's used for a particular purpose. So these are all examples that are proposed uses of blockchain technologies. Many of them are many of these uses are more effective than others, and come with many caveats. But at any rate, there's a lot of potentially promising applications. On the other hand, today's blockchain technologies, at least the ones deployed currently, are all severely limited in a lot of ways. So the public ledgers like Bitcoin and Ethereum are very slow, inefficient. They provide only weak probabilistic consistency, etc. And most of the private or permissioned ledgers effectively weaken security in various ways, reintroducing single points of compromise. And so I think these are all important good steps along the path of building truly secure, reliable, distributed systems, but the point is we're not there yet. We have to keep working to build what we really need. So that's basically the introduction. I want to focus in this talk so in the rest of the talk, I want to hit on three main points. First of all, the general challenge of making these systems more mature, in particular more scalable and secure and functional, and some steps that my lab has been working on in our research, and how they fit into how I see the big picture of developing decentralized systems. And then I want to look specifically at the problem of managing membership and fairness, and what does fairness mean in a decentralized system. And then finally, really looking forward into areas that I think we're just basically starting on in the blockchain space, and that needs to learn a lot and interact with the kinds of research areas that, for example, Pedja has talked about in terms of how to allow people to use decentralized systems such as blockchains to interact with each other in effective ways. That's an area, I think from the system building side, we're just starting on, and the system building side needs to meet the theory side and figure out how to put all the pieces together. Okay? So let me grab that so I can keep track of time a little bit better. Okay, so first of all, scalable, secure coordination. This'll in this part of the talk, I'm gonna, my lab's focus is on building systems, prototyping new system designs. I'll try to keep it fairly high level, and provide an overview. But I'm happy to talk about more low-level details later with anyone interested. And feel free to, of course, interrupt me. I see. Great. Yeah. Thanks for the questions. Yes, so there are very important differences in the architecture of different cryptocurrencies, but there's a huge kind of variety of emerging, developing ones out there. Most of the deployed ones are Bitcoin with a few very minor tweaks. So most of the deployed ones are not that different, that I'm aware of, but we are gradually seeing more divergence and more adoption of more ambitious, different schemes, so let me come back to the other question about applications. That's a really important question. Which applications are most promising? I'll touch on a few later in the last section of the talk, but that's definitely an open question too. So to me, what this boils down to is we're trying to implement the distributed trust principle. And like I said, this is nothing new. The fundamental idea is to have algorithms in which you can have a few or many different nodes or people working together in such a way that even if one or a few of them are maliciously misbehaved, you still get, you can kind of ignore them and move on and still get correct results and still get a secure system. And systems like Byzantine consensus and threshold algorithms like threshold cryptography, these are huge classes of algorithms that embody this principle in different ways. And these algorithms, again, are not new. They've been known in computer science circles for decades. But what I think Bitcoin did most importantly was to be the first successful system to create a system that was in principle open for anyone to join, right? So most prior threshold and distributed trust algorithms assumed that there was a fixed set of nodes that had somehow fallen out of the sky, or a system administrator a trusted system administrator had defined. So Bitcoin said, okay, anyone can come join whenever you want. And then secondly, it was designed to be scalable, so that thousands or tens of thousands of people could come and participate in the fundamental consensus algorithm and creating money, mining Bitcoin, which is creating money. And so you know, the architecture enabling this was extremely interesting, but it also kind of monolithically conflated a lot of issues together in ways that are still harming and causing a lot of confusion. So yeah, good question. I'll come to where the value of Bitcoin comes from in a couple minutes. So how does Bitcoin work? The most important kind of technical part of any distributed blockchain protocol, and where a lot of the discussion and research is on, is how the consensus protocol works. Now, how does Bitcoin's consensus protocol works? It's a crazy, very simple and beautiful, but very different from the way classic computer science consensus protocol works, in that it's completely probabilistic. Everybody who wants to participate is running a crypto lottery all the time, trying to generate random blocks, cryptographically hash them, see how many 0 bits comes out in the hash, and that defines whether you've won a winning ticket or not, right? So everybody's constantly doing this work, but when you get a winning lottery ticket, you get to add a block to the chain. But of course, sometimes either innocently or for malicious reasons, two parties might get valid-looking blocks at about the same time, and you have a conflict, history conflict. And Bitcoin says, classic consensus protocol said, okay, this is terrible. We have to very carefully design the algorithm to avoid this ever happening. Bitcoin took a very different approach of saying, relax, let's let this, let's not worry about this immediately, but just solve it down the line in a statistical fashion. So in this consensus protocol, when a conflict of history, when we've got two forking histories, we just let them both exist, but then different subsets of the network will be working on trying to extend both of the competing histories in some proportion, doesn't necessarily matter which one, and at some point one of those competing histories will be extended with another block, and statistically it's likely that one of them will be before the other. And everybody has a rule of always trying to jump to the chain that has the most aggregate work, the longest chain rule. And so in this case, if block B wins and gets it extended first, block A basically gets eliminated from history, and the system generally resolves. So so this is a really interesting, kind of design, but it also has some very practical problems and limitations. For one thing, it makes consensus extremely slow. You have to wait, more or less 10 minutes to minimum, and you're recommended to wait more like an hour to wait until a transaction you care about is buried like 6 blocks down. And because everybody's doing all of this at the same time, everybody's repeating everybody else's work, it provides really low throughput, right? So we and many other labs and companies around the world have been working on, trying to fix this. Coming up with different answers to how do we scale blockchains like Bitcoin. And scaling a little bit is pretty easy with minor tweaks, but scaling it a lot by orders of magnitude is much harder. And so I want to focus on the latter goal, which is what my group has been focused on. This really started a couple of years ago with a project we called Bizcoin, which tried to build on the Bitcoin's architecture in a more or less backward compatible way, but replace the Nakamoto consensus with a classic Byzantine consensus algorithm called PBFT, Practical Byzantine Consensus. By doing this, we were able to get the throughput, increase the throughput by a couple orders of magnitude and get immediate commitment. So when a transaction is committed, under the security model, it'll stay committed. Yeah, by the way, great question about mining introducing inequality, and I will definitely come back to that. So let's look at the basic challenge. How do you, the impedance mismatch between Nakamoto consensus and classic Byzantine consensus algorithms like PBFT. Basically, there were two problems with classic consensus algorithms. First of all, like I mentioned, they assumed a closed group was well defined rather than the open model that Bitcoin operated in. And second, classic algorithms typically assumed that that group was very small. Like usually they were tested in groups of 4 because that's the theoretical minimum in the classic Byzantine consensus model. And so without getting into too many technical details, I just want to give you the high-level intuition about how Bizcoin addressed these problems, and we can discuss details later, or you can look them up in the paper. So Bizcoin said, okay, for now anyway, even though mining is terrible, we're going to keep mining for now in Bizcoin, but instead use this cryptographic lottery proof-of-work mining to create not immediately committed blocks, but rather the proof-of-work miners are going to be mining for shares in a consensus window. So there's still going to be a proof-of-work blockchain. But that's not going to contain committed blocks immediately. But anytime a proof-of-work miner gets a new block, we have a sliding window of shares that moves over. Somebody loses a share, the new miner gains a share. And this defines the current consensus group in the classic PBFT sense. So this is a way to use classic mining to create an open system in the same way that Bitcoin is open. But to define a consensus group compatible with classic Byzantine consensus algorithms, right? And so that was, that's one technical challenge. The other is the scalability challenge. So how do we make classic Byzantine consensus algorithms work efficiently, not just for 4 or 10 participants, but for thousands? Because, even when we're just using a sliding window, we want that window to be big enough to be a good statistical sample of the recent successful miners, so that it's representative of the hash power. And to make the fundamental problem with scalability is classic Byzantine consensus algorithms typically have these two-phase, multiple phases where everybody has to persuade everybody else more or less independently that they're okay with whatever the current leader has proposed, and they're ready to continue with either the prepare or commit phase. So again, I won't get into the details, but the gist is this is kind of an order n squared communication and attestation and authentication problem if you implement it naively. And basically what Bizcoin did was use some other previous work that we had done the year before that on building very, very scalable, efficient aggregate signature schemes. So you could build a temporary tree, kind of like a video broadcast tree or something, but you could use it not only for multicast outward, but you could use it for aggregating collective digital signatures going up the tree. And so this enabled, in each round, enabled us to use very little communication or coordination per round to allow the leader to collect sign-offs from everybody in the group efficiently, compress them together into one small cryptographic unit, and then just broadcast that evidence back out so that everybody doesn't have to check everybody else's individual signatures or sign-offs, but just has to check one aggregate signature. So again, these are just scalability increasing mechanisms, and there are many other ways to increase scalability too. For example, that Marco will talk about and that other groups are exploring. But anyway, so back the upshot is, again, this allowed us to improve the scalability of Bitcoin-like systems about a couple orders of magnitude in throughput, as well as get the commit times down from tens of minutes down to tens of seconds, basically, 5 to 10 seconds. But that was, of course, just really the first step. The other main scalability, huge scalability problem, like I alluded to before, is that in most current blockchain architectures, all of the main consensus nodes are kind of repeating all the same work. Everybody's doing everything in terms of verification and checking everybody else. And as the system grows big, this is more than necessary. And it means that you don't get more throughput or aggregate capacity as you add more, more resources, more participants and stuff. So we really want to balance the redundancy. We still want some redundancy for distributed security, but not so much redundancy that we don't actually get any scalability or improvement in capacity as we add participants. And so horizontally scaling was the goal of our next step in the scalability space, and this is a paper called Omni Ledger that we just presented a couple of weeks ago in IEEE Security and Privacy. It's turning out that a lot of companies and startups especially are expressing interest in implementing blockchains along these ideas. The basic idea, we didn't come up with the basic idea known as sharding, the idea that if you've got a very large number of participants, you'd like to break them down into smaller shards, each of which is big enough to be secure, but small enough so that you can have a few shards, or perhaps many shards if you have a sufficiently large number of participants to start with, and each shard should collectively do only a portion of the work. So like one account, one Ethereum account or one Bitcoin account might be assigned to one particular shard, right? So that's the basic sharding intuition. We want to break the big system into shards, each of which manage as a subset of the total system state. This creates two main challenges. First of all, creating those shards securely. The problem is if you allow an attacker to choose or even just bias the choice of members in those shards, then the attacker can stack one of the shards to their own benefit and take over, right? So we need very strong bias-proof randomness to actually create those shards securely. And that's the purpose of another protocol that we developed and presented in the previous year's Oakland called Randhound or Randherd, to create a strong, scalable, bias-resistant randomness. So that was one of the problems. The other problem is what happens when you have transactions that have to affect multiple shards atomically. You want to make a payment that collects, Bitcoin or tokens from two or more shards and pays them to a third shard or something like that. You want to make sure that all of those pieces of the transaction either commit or abort atomically. You never want to have just one part of one handled. And so I won't get into the details of that, but that's the other problem that Omni Ledger addresses, right? So the upshot is that with this additional level of horizontal scale out, depending on the security parameters you want to set, So you can configure the system for different trade-offs between the number of colluding malicious nodes, or the percentage of colluding malicious nodes you can tolerate, versus the total participation, and get different trade-offs in terms of final throughput. And so, for example, this is where we assume a fairly weak attacker who can only control at most 1% of the nodes. We've shown, this is in a testbed environment, we can show that we can get really high numbers for much more conservative attack models with like 12% or 25% attackers. Of course, that reduces the throughput we can get in this testbed, but the real point is that we get this scale out. The more resources you add to the system, the more participants you add, the more throughput you get. And so the limitations of the lines here are really limitations of this testbed deployment and not with the fundamental algorithm. Okay. So I mentioned that a real important subpart of this problem is randomness. And how do you, so randomness is critically needed not only in Omni Ledger, but actually for many other purposes, for many other distributed and decentralized algorithms, including things like risk limiting audits in voting systems, or sortition. There's a lot of interest in sortition-based collective approaches to collective intelligence. But many other purposes. But distributed randomness is a very hard problem, actually, technically. It's surprisingly hard, and it's a problem that a lot of institutions keep getting wrong. So, it's soccer time. How many of you remember one of the many Fifa soccer scandals when it was discovered they were biasing the randomness of that was used in the player election process? This was a few years ago. And there's a repeated tradition of major lotteries getting hacked. The latest one was just in the New York Times like a week ago or so. So this is a very big practical problem. In the interest of time, I won't get into the details of that, but there's there's kind of various naive approaches that you would think would work and really don't. Either they're really broken, or just not secure, or not bias resistant, or not scalable. There are existing ways to do that, which definitely do work, but the challenge is to really make them scalable, and that's what we've been focusing on in this set of randomness protocols that we've been building. So, sorry if I'm missing. Yeah. So I'll come back to the application-related questions later. But feel free to interrupt me if there's kind of any particularly topical questions that I need to answer now. So I've been talking about blockchain scaling. What are the next problems? So what's the future in this space? Well, it's hard to predict, of course, and we'll get other perspectives from Marco and others. But to me, I see decentralized systems diversifying more, kind of in the way that we've seen hardware systems, our processor architectures diversify into many different functional units. I think we're going to start seeing decentralized systems that have shards of many different types, shards specialized to different purposes, kind of like modern systems have CPUs, GPUs, tensor processing units, etc. Right? And just as one step in that direction, one of our ongoing pieces of work, there's a preprint out there on this, but it's not published yet, is a way to create a second kind of shard for managing secrets. So we still have the existing blockchain shard that manages the integrity, uses consensus to manage the integrity of information and records. but current blockchains you can't entrust a secret to a current blockchain. You have to entrust the secret to somebody off the blockchain. And maybe with zero knowledge proofs or snarks, you can prove stuff about that secret and put that on the blockchain, but you can't really entrust the secret itself to the blockchain securely in a decentralized fashion with current systems. And so Scarab is basically trying to fix that by creating a second kind of shard that's just as distributed as the integrity enforcing shards of current blockchains. But you can actually literally public key encrypt a secret to it, write it in a transaction to the blockchain along with a policy, and have the system provide distributed enforcement of the access of that and accountability for any way that secret is used, to ensure that however that secret is used, it leaves a record where there's no single point of compromise that can compromise either the integrity or the privacy of that record. Right? So again, I'll skip the details, and then but then another, I think, really
But why can't you encrypt the secret and then use the blockchain to?
Yeah, good question. So the obvious base case is I could say just PGP encrypt something to your public key and Aaron's and whoever I think should be able to access it, right? And put the ciphertext on the blockchain. But then I have, at the time of putting it on, I have encoded the secret to a particular set of receivers. Now, if that changes, say, Aaron gets fired, or something, right? I can't revoke that key. And if any of those private keys ever leaks, then the attacker can decrypt the secret without even leaving a record of that the attacker made that access, right? So so that doesn't provide either revocability or strong accountability. The other common approach that I know many blockchain projects are using is just entrust the secret to a data storage service, a centralized data storage service off the blockchain, which promises to keep it safe and promises to record any accesses on the blockchain. But that's again a single point of compromise. If that gets compromised, then the attacker gets the data without any records going on the blockchain, or things like that, right? So this is the point is to provide decentralized enforcement of both the integrity and the privacy, the confidentiality. Yeah, good question. Hey. So other issues I think we need to be looking at in the larger scalable coordination problem are, how do we pick shards, and can we pick shards for more special purposes, for particular properties such as locality, and make localized shards much faster. Of course, that can create security problems if a lot of the participants in one place are colluding together, then that might inherently be, in some sense, a compromised shard. How do we deal with that? And we've taken some steps in the Omni Ledger architecture to what we call trust but verify shards, but there's a lot more work to do in that space. And so we have a sub-project looking at locality-based sharding, but again, that's preliminary. Okay? So that's kind of an overview of the scalable coordination part. I want to see if there are any questions particularly pertaining to that, or anyone feel free to speak up if you have a question specifically about the first part of the talk that I should address. I think most of the others are good to come back to later. Okay, so that's the first part. Now the other two parts will be quicker, hopefully, and in some sense a higher level. So we've been building these pieces, building blocks of more scalable, decentralized systems. How do we use them? And in particular, how do we manage membership and fairness? How do we make open systems that are fair in some sense? And how do we govern them and manage their incentives, right? And so And these are much more open, unsolved problems. I think this is where I'm really interested in a lot of the future work, as opposed to having produced solutions so far. So what is fair in a blockchain sense? That's of course very subjective. Kind of in some respect it's fair if you think it's fair, and if it's not fair you cry, or hopefully not, but it's endlessly debatable. So regardless of your definition, in any organization, you've got to have a way to decide who the members are that can be involved in decision making, and how much power does each member get in some, how much weight, how much voting power, right? There's always, you always have to have some form of this membership and weighting. And as an example, how does Bitcoin define this? So I briefly talked about the mining problem, but let's now look at that mining not from a consensus algorithm perspective, but from a fairness and membership perspective. So I say that Bitcoin is a membership by hazing ritual protocol, just like a fraternity. So, you want to join a fraternity, you have to do something uncomfortable and embarrassing, typically, right? Something involving work that, maybe you don't want to do, at least not all the time. And of course, in fraternities, there are a lot of different kinds of hazing rituals. If you've been to MIT, there was the classic hazing ritual from the 50s where these students used Oliver Smoot, another student, an inductee, to measure the length of a bridge. And to this day, the Smoot markers are there showing how many Smoots long this bridge is. And so, a hazing ritual can be anything. And in fact, in the island of Yap, there was a culture that developed to chisel giant coins out of rock that was only available at the next island, that they had to laboriously chisel and carry back over for no other purpose other than to be able to show that they were able to do it. They were able to muster the manpower to do that, and then that became a notion of value and currency, something they could buy and sell, sheep and goats or whatever it was they bought and sell there, right? So Bitcoin is just like that. It's just creating value by making people do unnecessary work that's unnecessary for any other reason, namely digitally flip coins and solve hash crypto puzzles. And you have to do that, forever, continuously, if you want to keep mining Bitcoin or maintain your membership. And your reward and your membership share is proportional to the hash power, the number of hashes per second you do, right? And this is again directly related to the value. The more mining share you get, the more currency you get to print, right? So. And if you want to keep getting rewards, you got to keep mining. You got to mine more to keep up with the Joneses, to keep up with the competitors, right? Unfortunately, this has caused a really bad effect environmentally, in that it's basically a currency backed on energy waste. The more this race to waste energy, prove you wasted energy. And now, as a result of this, Bitcoin is consuming a lot more energy than many countries are using for productive uses, right? And so this is a terrible thing from an ecological perspective, and it's not even really succeeding in keeping Bitcoin decentralized, in that there's so many re-centralizing incentives that cause the top 2 or 3 mining pools could easily break the network, because they have a majority of hash power, right? And most cryptocurrencies that are actually deployed are not really that decentralized. So what are the alternatives? Now, there are a number of alternatives. One is called just permission ledgers. Let's just go back to assuming somebody, like an organization, a federation, defines who the members are by sitting around the table and agreeing on that. And that's actually a reasonable way to do things. And a lot of permission ledger systems like Hyperledger use this, and actually, we're using that in a bunch of our practical applications as well. But it's no longer open for anyone, right? So it's and keeping a system open to anyone, I think, is one of the big challenges. So I want to get back to that challenge. Many people in the cryptocurrency and blockchain community are interested in this alternative called proof of stake. And because I see I'm really running low on time, I think I'll skip past some of the details. Basically, the idea of proof of stake is you buy existing shares, buy some amount of the existing currency or shares in the system, and then use that to represent voting power, right? It's a technically interesting and non-trivial problem to solve this in various ways. It relies on certain agreement properties. You have to be able to have everybody agree on the current set of stakeholders. It relies on distributed randomness to sample a set of those stakeholders in a secure fashion and statistically representative fashion. And then it requires everybody to be able to verify what the current state of the universe is, even if they're coming online from the start or have been offline for a long time, right? And so a lot of the technical challenge of building secure proof of stake are in solving those problems. I think we do have the tools to do that. That hasn't been our main focus, but we have one way to use more or less the tools we already have to build a secure proof of stake system, and there are other approaches like Algorand or Ouroboros that you can read in the literature. So, so I talked about the secure randomness. The other kind of important piece of the puzzle is the verification, which another of our recent work called Chainiac actually addresses it by making blockchains cryptographically verifiable and traversable using collective signatures, both forward and backward in time. And it has kind of a skip list like property for efficient traversability for long periods of time, either forward and backward. But again, I'll skip the details. And I think this kind of thing has many applications other than proof of stake, such as for certificates or applications where you want to scan a certificate and maybe offline, or distribute software updates offline and have devices be able to verify that they are on the blockchain, that a large group of nodes have witnessed and signed off on them without trusting any particular node. So, just to. So that's another piece. But anyway, so the point is we have the pieces we need in general to build secure proof of stake. Now, how interesting is that? And the reason that my lab hasn't been focusing primarily on proof of stake is that I personally don't think it's all that interesting in the big picture, because proof of stake just reinvents the shareholder corporation in a very fundamental sense. And so if shareholder corporations didn't already fix the world, then proof of stake won't either, right? Because all of these are just proof of investment. The more you invest in whatever, in work, in stake, whatever, storage, different systems, the more you get back. And these all will have re-centralization effects, which basically amount to new flavors of the rich get richer maxim, right? So the real question to me that we need to be working on is, how do we decentralize in a way that will stay decentralized and not re-centralized, like proof of work and proof of stake, etc. And so this is where one of my deepest interests are in continuing work. So we've just taken a few steps in this direction, but it's mostly still an open problem. The best way I can see of creating open decentralized systems that can actually stay decentralized is I think we have to incorporate democratic principles. We've got to somehow enforce one person, one vote type provisions. And one of the approaches that I proposed quite a number of years ago is called Pseudonym Parties, which is to use a physical security foundation to basically make people prove that they're real people by showing up to a physical event. And there are a lot of details, of course, to be worked out. But the idea is, if you have an event like this, or you have many events like these that are synchronized appropriately, across different countries or different parts of the world, then anybody can show up to the local one, but they have to be in the room at a particular moment. Because we still, for the moment, only have one physical body, we're only going to be, each person is going to be able to be in one of these rooms at a time, right? And then we just leave with a token saying, you know, I'm a real person. But you only get one of those tokens, right? So, and you don't need to be identified. You don't need to identify people. So this is a thread in the kind of the research program that Pedja mentioned, accountable anonymity. Can we create digital identities that are not identifying at all, but just accountably say, you know, whoever holds this is one and only one real person, right? Without actually saying anything about them. So this is an ongoing problem. Of course, that brings massive, you know, important scaling problems as well. How do we federate and scale many pseudonym parties so that they remain both secure and we can create assign these tokens so that they're interchangeable and usable across countries, across the world, right? And so, you know, we're exploring that, but again, it's an ongoing problem. Other groups are exploring other ways to do this. For example, there's a project that's trying to use online video chats for this, and various others that are exploring, you know, web of trust kind of approaches. And so those are interesting as well. The point is we need to be exploring several of these approaches and developing them, because for you know, decentralized systems of all kind, we desperately need, of course, we need to get rid of proof of work immediately, you know, as quickly as we can to avoid the ecological disaster that it's causing. Proof of stake would be better, at least for that purpose, or going to permission systems. But in the long term, I think we need something more like proof of personhood, or a true long-term foundation for decentralization. Okay. Yeah, so, so one of the questions was, doesn't mining produce inequality? And yes, it does, massively. So that's part of the point. In fact, there's a fantastic article that went recently by a startup that was trying to create new mining hardware and compete with the existing established players in Bitcoin mining hardware, and observing all of the advantages of scale and advantage of being able, the dirty tricks that the, you know, bigger players could play. Basically, it's you know, there's a huge range of ways that the bigger players can, you know, can lock out smaller players, make their shares get even bigger, and, you know, continuing to the re-centralization and yeah, you know, the rich get richer effect. And so to create a system that, you know, does not, you know, always advantage the big players, that's a very unnatural thing. That's pushing the stone uphill. That's, you know, so we have to design a system, in a sense, as a very unnatural system explicitly to do that. And, you know, that's what I hope some form of proof of personhood could do, but it's a very, very hard problem. Okay. So, and I know I'm just about out of time, so I just want to briefly talk about, so again, bringing the perspective up a further level of abstraction. Supposing we can create, you know, these scalable, decentralized foundations, and supposing we have better foundations for membership and fairness. What can we do? And I just want to, and again, this part is completely future work. Like, you know, we've managed to do little to none of this, but I just want to map out what I see as the big challenges, what I think we need to do most urgently and most importantly with blockchains, and build on them and for development, right? So any kind of organization throughout history has to have governance. If governance collapses, the organization collapses. That's you know, kind of, we've seen that, you know, consistently throughout history, including in the Bitcoin community. So there's this repeating question: can blockchains self-govern? Can a decentralized cloud of Bitcoin people or Ethereum or whatnot govern not only the operation, but the future evolution of the system. And this has been a big problem. A common kind of naive perspective is, we just need more blockchain, more, blockchains can solve everything. We just need more of them, or put more trust in it. And again, I think that's naive. And I think we've seen that play out, for example, in the Bitcoin community, where the general attitude has been, Bitcoin doesn't need governance. We've got miners and developers and stuff like that. And so what that means in practice is that for simple, uncontroversial decisions, consensus in a governance sense is basically the what the developers decide to do. But if they can't decide what to do, like in the block size debate, so hopefully you're all familiar with the classic story Gulliver's Travels, in which there was this war between the people who wanted to break eggs at the big end and those who wanted to break eggs at the little end, right? We've been seeing, we've seen a similar version of that in Bitcoin, where one faction wanted to increase the block size to get a marginally more scalability, more throughput, and the other said, no, for philosophical reasons, we want to keep the blocks small. And basically, there was no way to create this decision. Bitcoin had no governance structure, even to decide on something as simple as 1 megabyte or 2 megabyte blocks. They needed a 1-bit decision, and they couldn't do that, right? And so, other blockchain and cryptocurrency systems have learned from this decision, but largely addressed them by, in some sense, re-centralizing. Like Ethereum and Zcash have foundations that have a very much more centralized decision-making structure. This is fine, pragmatic steps forward, but it leaves the open question: can we build blockchain systems that truly are and remain decentralized in terms of governance structure as well? So this is a huge challenge, in part because there's a huge open design space. It's hard to know how should we design it, and if we get anything wrong and don't have a backup mechanism, any single bug can be completely fatal to the system, because anybody exploits one governance system bug and boom, they take over the system, right? So we need to figure out how to do that. Getting back to the fairness membership aspect, we need to do it in a truly fair, decentralized way. For example, using a truly democratic one-person, one-vote aspect. So, and it's not just about, like Pedja actually mentioned, to echo that, it's not just about voting either. Decentralized systems have to have a foundation for membership and power. They have to be able to recognize and differentiate real people from fake people, from fake accounts. They have to have good decision-making capability, but also information gathering capability. How do decentralized people process and aggregate large amounts of information? And they need incentives to do that. And so I would say these are kind of the 4 really critical categories of development we need further in ongoing decentralized systems. So. I'm out of time, so I'll just quickly go through this. Just quickly touching on the information gathering problems. So this is another area where I think having a strong decentralized foundation, such as proof-of-personhood, could help in, say, collective intelligence, and is desperately needed to help be able to fight, address the Sybil problems or fake news and things like that, where there's this huge risk, huge problem of attackers being able to amplify fake news or trolling by upvoting with 10,000 botnet accounts, right? So I fully think that collective intelligence systems, well designed, can be resistant to trolls, but only if the trolls can't amplify their power by 1,000 times or 10,000 times with Sybils, right? So fundamental tool we need to develop there. And then again, echoing a topic Pedja mentioned, I think it's important in these information gathering mechanisms to have both anonymity to ensure strong freedom, as well as accountability to be able to resist trolling and these kinds of attacks. And we and others have been working on various research projects in this direction. For example, AnonRep, a system we built a few years ago, that prototypes a anonymous reputation system. This wasn't a blockchain paper. It wasn't called a blockchain paper, but it was basically creating kind of a proto-blockchain in which each participant could anonymously maintain an account, kind of like a Bitcoin account, but that acquires reputation scores, acquires likes or upvotes or something like that. And then you can later post a message that's nobody can link to the previous messages, but you can say, but this comes from someone with at least 100 or at least 1,000 prior upvotes or something like that, right? So it was just a preliminary proof of concept of one of many, many ways you could potentially create blockchain-like reputation systems or reputation systems in this securely decentralized model. But again, a lot more needs to be done in this space to make it really work. And finally, getting back to Bitcoin, I think one of Bitcoin's big conceptual contributions was showing how you could build a decentralized system that's self-incentivizing, that has an incentive structure built in, a reason for people to use it, in this case mining, either because it's cool or because you want to make money off of it, or different things. But of course it has these major flaws. But then this leads us to the question, what are more reliably decentralized and more say, democratically decentralized incentive models that we could develop? And again, I'll just leave that as an important question. So another one we're just starting to explore. For example, how can we design new cryptocurrencies with more democratic foundations in a decentralized fashion, and that will ensure fairness both across a population and across time, across years and generations, right? So, and there's some really fascinating connections between this and ideas going around such as universal basic income and stuff that we can get into some other time. So can we create permissionless universal basic incomes on top of blockchains? So anyway, I just want to suggest those as some of the most important, from my perspective, areas for ongoing work, and the most important things we need to figure out how to build with and on decentralized systems like scalable blockchains, right? So sorry for going a few minutes over. So in short, in summary, we're gradually learning, I think we have most of the tools we need to build reliable, secure, decentralized systems, but they're still very, not mature, not really easily usable. And actually connecting these systems tools and foundations to applications and higher level organizational and governance structures is a hugely important open problem. Okay, yeah, so thank you. And I'll let you decide whether there's time for any further questions or you want to defer them to.
Yeah, a few minutes, it'll take a few minutes.
Okay, thanks.
We'll just go through the questions because...
Yeah, so let's see. Are they sorted by, okay, good. A proof of work system where the work is done is useful. Yeah, really good question. And quite a few people are asking, thinking about that and trying to create useful proof of work systems. Unfortunately, I have not seen one that is convincingly, that I think is convincingly secure or even plausibly secure. Other than systems that end up relying in some other way on either falling back to relying on proof of work somewhere else, or some other very non-decentralized trust assumption, like trust Intel SGX, to do the right thing, and then you're just trusting one central party, namely Intel. And the fundamental problem with doing proof of useful work is who gets to define what useful means. Somebody has to, whatever work is done, somebody has to somehow judge its utility. And then, when you think about algorithms to judge that utility, well, somebody has to vote, or, that is a collective intelligence problem itself. And you end up having to add up opinions on how useful or whether this work is useful. And then how do you add up those opinions? Well, you don't have a Sybil-resistant foundation with which to add those values. And now you're back at the problem you started with, the Sybil attack problem you started with, right? So I have not seen a single proof of useful work that doesn't have that fall into that fundamental circularity trap. So, and I would love to see one, but I'm extremely skeptical that we will see one. I just don't think there's a magic bullet. Questions that distributed ledgers can help address. The why question. Can blockchain help understanding the rationale behind distributed actions and decisions? Yeah, so actually that's a great question and observation. I think we're already seeing, in some sense, because of the enforced transparency that the Bitcoin-like blockchain model creates. If you want to use Bitcoin, you got to put all this data out on the ledger that everybody has a copy of, and then there are innumerable ways anybody can look at that ledger and analyze it. And from a analysis and scientific understanding perspective, that's great. And there's a lot of groups that are doing really good work, analyzing what's on blockchains and things in different ways. Now, that will be, the effectiveness of that going forward will, of course, be in somewhat tension between kind of the analyzability and transparency and the privacy measures. If you want to put something private, you put zero-knowledge proofs instead of about the data instead of the data itself, or things like that. Then that makes it harder to analyze the the blockchain. And we need to and again, that's, I think, figuring out the right balance and the right ways to put enough data on the blockchain to facilitate analysis while maintaining privacy is one of the big ongoing challenges we have to work on. So, okay, yeah. Thanks a lot.